This is Gary Anderson, and this is a walkthrough of my 2017 quadratic chapter for advanced algebra. The test that's given in 2018 will be very similar. Because we have a somewhat shorter block, the last two pages for the calculator, the 3x3 matrices, taking 2 points and fitting it to a line, and the solving 2x2 will be optional. If you can get to those, then those are questions that will be on the final exam. And if you pass them here, you can use those questions if you make a small mistake on your final exam. Only those finishing the basic part of the Chapter 5 test will need to work on those. Okay, for this problem here, we need to find the vertex using the appropriate formula and then graph the parabola. Well, so it kind of makes sense in this case here for us to approach it like we do the quadratic formula to find the axis of symmetry. So we first write down A, B, and C, and then we remind ourselves that the formula minus B over 2A returns the x-coordinate of the axis of symmetry, or the x-coordinate of the vertex. So minus B over 2A, we write that down. Substitute in the values for our formula. I like using parentheses here, so I am careful about the negative sign. So 4 over 2 reduces to 2, so our axis of symmetry is x equals 2. To find the y-coordinate, we plug that back into our original equation. So replace x with 2. 2 squared minus 4 times x. 4 times 2 is minus 8. And then subtract the 3. And that returns a value of y equals negative 7. So our vertex is 2, negative 7. We go ahead and plot that point. And we also then will plot the y-intercept and the reflection across the axis of symmetry, which brings us over to the point of, let's see, 4 and negative 3. And those 3 points plotted on the graph are right there. Okay, again, for this problem here, we'll need to find the vertex and plot the graph. So just like we're beginning the quadratic formula, we will get the coefficients and write them down. And then we remember that the x-coordinate of the axis of symmetry is minus b over 2a. Go ahead and plug those values in, and we get a value of 7/2. So minus 7 over 2 times negative 1. We go ahead and we plug in the x value of the axis of symmetry into the original formula to get the y value. Notice here that when we square 7/2, we get, or actually on the right-hand side, it looks like what we're doing here is we're taking the linear term, that becomes 98 over 4, or 49 over 2, which is 98 over 4. On the quadratic term, that's going to be minus negative 49 over 4, so we'll combine those together, and we get positive 49 over 4, then we'll subtract 2, which can also be written as 8 over 4, and so that becomes 41 over 4 is the y-coordinate of the axis of symmetry, and then that gives us a vertex of 7/2 and 41 over 4, which we go ahead and we graph. Notice here that the y-intercept is negative 2, so there's another point at negative 2 reflected across the axis of symmetry, so we have 3 points and we can graph the parabola. Okay, and then our third problem here, again we're asked to find the vertex and the axis of symmetry. Hopefully you see that since there's no linear component, our negative 6 for our y-intercept is also going to be the x-coordinate of the axis of symmetry. And then you can go ahead and just plug in a couple more points and graph this. But let's go ahead and just proceed on this one as if you're using the standard formulas we use for the other problems. So in this case, we go ahead and we write down all of the coefficients, remembering that b is equal to 0. Our x-coordinate of the axis of symmetry is minus b over 2a. So this is going to be minus 0 over 2 times 1/2. The student that did this didn't show their work, so I'm showing that. So x, therefore, is going to be equal to 0, as we expected. Then we go ahead and we plug the value 0 back into the original equation to get the y value of the axis of symmetry. That produces negative 6. So we have a vertex of 0, negative 6, and here's our graph. Notice here to get 2 other points for the graph, you can just plug in a value for x. In this case, I can plug in 1, and I get 5.5. I can plug in negative 1, and I get negative 5.5 also, and we can connect up those points. You can also use any other values of x that you'd like. And as we've discussed in class, the a value of the or the quadratic coefficient tells you how much the graph changes if you move 1 unit to the left or the right from the vertex. Okay, for this problem, we're asked to find a complex number that has an absolute value between 3 and 8. And here the student proposes 3 plus 4i. So let's check that out. So we'll go ahead and we'll graph the complex plane with the real value on the horizontal axis and the imaginary component on the vertical axis. And so that gives us the point 3, 4. Let's go ahead and use our definition of the absolute value, which is the distance from the origin, to go ahead and connect that with a line. And we'd like to see the length of that new line that we've created. So we'll recognize that we can make this into a triangle where the horizontal distance is 3 and the vertical distance is 4. So our absolute value is going to be equal to, using Pythagoras' theorem, the square root of 3 squared plus the 3 square root of, or plus 4 squared. So that's going to be the square root of 25, which is equal to 5. So that checks. That does give us an absolute value between the values of 3 and 8. Okay, for this problem, we're asked to write the complex number in a plus bi form. Remember, complex numbers are no more complex than any other numbers. And so in this case, we manipulate the expression the same as if I were not a number, but rather a variable, and we just combine like terms. So here we just have to be careful about distributing the negative sign. So we draw our little arrows, and that gives us 3 plus I minus 7, and remember we have minus 6i. Then we go ahead and we group the real terms together and the imaginary terms together, and we write our answer as negative 4 minus 5i. Okay, here's another, again, straightforward problem. Once you recognize that complex numbers are no more complex than any other numbers, and they work just like every other expression in algebra. So here we're adding 2 complex numbers together. We'll go ahead and just get rid of our parentheses. In this case, we don't even have a negative sign to distribute. So here are all 4 of our components. We will combine our real components and our imaginary components. So negative 4 plus 5 and negative 9i minus 7i. That's going to give us 1 minus 16i. Okay, for this problem, we're asked to simplify an expression that will result in a complex number. In this case, our student proposed going 4 plus 3, and then she did the square root. She recognized that 25 was 5 squared and negative 1, which she then separated out and wrote 4 times 3 times 5. She brought the 5 squared out of the square root and wrote it as 5. And then she recognized that the negative 1 would turn into an I. In class, we presented it more like this, where we rearranged and wrote out each square root separately. So we're going to have 4 plus 3 times the square root of 25 times the square root of negative 1. So that's going to give us 4 times 3. Square root of 25 becomes 5, and the square root of negative 1 becomes I. And so that's going to be 4 plus 3 times 5, or 15i. Okay, here we're asked to multiply together 2 expressions, 2 binomials in a sense, and simplify them. So in this case, this student replaced negative the square root of negative 9 with 3i and the square root of negative 4 with 2i, which is perfectly fine. She then FOILed and got this expression here. And then recognizing that I squared is equal to negative 1, she was able to combine like terms. And the 6i squared becomes negative 6, minus 2 is negative 8, and then 3i minus 4i is minus I. Okay, the next two problems ask us to find the additive inverse of a number. That's the number that you add to an existing number to get you back to the origin or back to 0, or in this case for a complex number, 0 plus 0i. And it's very simple. All you need to do is change the sign of the real and imaginary component. So I think I would jump right to these problems if I was taking the test and get these two easy ones out of the way. So in this case, this works because for a plus bi plus negative a minus bi, you add the real components together and the imaginary components, and you get 0 plus 0i, which is right at the origin. So for our first problem, we'll just take the opposite of negative 2 minus 3i, and that's when we distribute, it's going to give us 2 plus 3i. And for the next one, we'll take the opposite of 1 plus 4i, just reversing the signs, and that's going to give us negative 1 minus 4i. Okay, next we're asked to do three problems where we're asked to find the absolute value of a complex number, and remember that's just the distance from the origin. And so in this case, here's an example of a graph in which, for 7i, in which 7 is plotted on the vertical axis. That's our imaginary component. So we're obviously just 7 away from the origin, and our answer is going to be 7. However, if you'd like to use the general formula, the absolute value of a plus bi is just given by the Pythagorean theorem. And so we can go 0 squared, because 0 is the real component, plus 7 squared. Add those together, that's the square root of 49, and that's 7. So for our second problem, again, we can just graph this. On the real axis, we get 12. There's no imaginary component, so our absolute value is going to be 12. If you'd like to use the Pythagorean theorem, it's just going to be the square root of 12 squared plus 0 squared is 144, so that's equal to 12. The next one is going to be a complex number written out, and we can use Pythagoras' theorem on this one here. That's going to give us the square root of 13. Notice here the student made a mistake and did plus or minus the square root of 13 because that's generally how you'd solve for x squared. However, remember that distances are always positive, so you should throw out the negative solution. Here's this number graphed on the complex plane. So we've got negative 3 and minus 2i. We need to figure out the distance from the origin, so we make that into a triangle, and we have a height of 2 and a width of 3, and then we can use the... Okay, next we need to solve a bunch of quadratic equations, and I really do want to caution you to use a variety of methods. Ideally, use the best method. You might be able to get away with using the quadratic formula for every problem, but the truth is you won't become a great math student unless you use the one that's most efficient. Okay, so in this case here, it's probably the best method would be to factor x squared minus 16 by using the difference of two squares. That's going to give us x plus 4, x minus 4 is equal to 0. And then we can recognize that our two solutions are either x equals negative 4 or positive 4. Another approach would be to use the method of square roots, and that is put the 16 to the other side and then take the square root. Remember to getting plus or minus the square root of 16, and so that's going to give us plus or minus 4. Either approach would be a good, efficient way, and hopefully you could choose between those with equal efficiency. Okay, for this next solving problem, we look at it and we say, hey, that might be able to be easily factorable because it's a trinomial and the numbers look clean. So we need to remember, combine our quadratic and our constant coefficient, multiply them together, and recognize we need two numbers that multiply to negative 10 and add to the linear coefficient, which is 3. So we think about it for a bit and we recognize that, well, minus 2 and positive 5, those multiply to negative 10 and add to 3, which means we can break up that linear component into two pieces. and get x squared minus 2x plus 5x minus 10. We factor out the x from the first two terms and the 5 from the last two terms. That gives us x times x minus 2 plus 5 times x minus 2. We can factor out the x minus 2, and then undoing the distributive property, when we do distribute, we get x plus 5. So that's now factored, and by the zero product property, we recognize that x can either be equal to 2 or x can be equal to negative 5. Okay, so looking at this problem, it looks like it'd be good to use the method of square roots. You could just subtract 48 and then divide by 3. In this case, this student chose to factor out the 3 first, which is a good choice also. And then she went ahead and divided both sides by 3, which eliminates the 3. She could have also kept the 3 factored out and it still would have worked. But this gives us x squared plus 16 is equal to 0. That can't be factored by itself, but you can move the 16 to the other side and then take the square root, remembering you get plus or minus. And then, of course, the square root of negative 16 is going to be the square root of 4i, giving us our final answer of x is equal to plus or minus 4i. Okay, for this problem, originally you might see if factoring will work. It doesn't look like this is an easy one to factor, because you're going to have to like factor out a 2 or something, and that gives us fractions. The student actually attempted to solve this problem by completing the square, which would not be a bad strategy, but she did make a computation mistake in the process. So I'm just going to use the quadratic formula. So in this case, I'm going to write down a, b, and c. A is equal to 2, b is negative 1, and c is equal to 1. So our axis of symmetry is minus b over 2a. Replacing b with negative 1 gives us positive 1. And 2 times 2, so that's going to be positive 1/4. There's a mistake in my answer key. I didn't divide by 4 in this part of our answer, but we got to it later. Our discriminant is b squared minus 4ac. So let's replace those values and evaluate. So negative 1 squared minus 4 times 2 times 1 produces negative 7. So because the sign is negative, we expect two complex numbers as our solution. And so we get 1/4 plus or minus the square root of negative 7 over 4. And that square root of negative 7 becomes the square root of 7i. And so our final answer is 1/4 plus or minus the square root of 7i over 4. Okay, so we need to write each function in vertex form. So remember, we can use minus b over 2a to find the x-coordinate, plug it in, get the y-coordinate, and get our vertex that way. And that's how the student originally approached it. And then next I'll demonstrate also using completing the square to get the vertex form, which is actually easier. So if we're going to use the original form, we write down the values of a, b, and c. We use minus b over 2a to get the x-coordinate of the vertex, which in this case is going to be negative 4, negative b over 2 times 1 for a, so that gives us negative 2. We plug that value in for y, and we get that y is equal to 4 minus 8 minus 7, which is minus 11. That means our vertex is minus 2 minus 11. That gives us a vertex form of y equals, she wrote down the 1, which is the a value, that's good. X plus 2 quantity squared minus 11. And then here would be the graph of it with our vertex. And notice that she has minus 7 for her y-intercept, and then she's reflected it to get another point to graph the parabola. A better way probably would have been to go ahead and move the 7 to the other side. And that's going to give us x squared plus 4x plus something. That something is going to be half of the linear coefficient 4, which is half of 4 is 2. 2 squared is 4, so we add 4 to the right-hand side, remembering also to add it to the left-hand side, so the equations balance. And that's going to give us y minus 11, and then the right-hand side factors into x plus 2 quantity squared. Okay, so here's another problem to put it in vertex form. And again, you have a couple choices, the minus b over 2a form to find the vertex, or by completing the square. Completing the square will usually be simpler once you're good at it. The student could have done completing the square, but she chose to use the minus b over 2a form. So let's see what we got there. Minus b over 2a minus 18 over 2 times 3, which is 6, produces minus 3 as the x-coordinate of the axis of symmetry. We plug that value into the original function to get 27. And that's going to then give us actually negative 27, so that gives us a vertex form of 3 times x plus 3 quantity squared minus 27. Remember that the 3 on the outside here comes from the original quadratic coefficient. And then we can, again, graph the vertex. Notice here that it goes through the origin, so you have an x-intercept at the origin, and reflecting that across gives you a second x-intercept. Now, if we were to use completing the square, we'd begin by factoring out a 3, so we get x squared plus 6x plus something. That something is half of 6 squared. Half of 6 is 3. 3 squared is 9. And if we add 9 to that side, how much have we increased the right-hand side? Well, we've increased it by 3 times 9, which is 27. So we add 27 to the left-hand side. And that means that y plus 27 is equal to 3 times the factoring of x squared plus 6x plus 9, which is x plus 3 quantity squared. Okay, so here we're asked to evaluate the discriminant for each equation and tell how many real and imaginary solutions we have. So remember, if the discriminant is negative, we'll have 2 complex conjugate solutions. If the discriminant is 0, we'll have 2 identical solutions. If the discriminant is positive, we'll have 2 real solutions. And if the discriminant is a perfect square, we don't expect any square roots in the answers, so we'll have 2 irrational solutions. Okay, let's go ahead and let's take a look at this one. Our discriminant is b squared minus 4ac. Our values for a are 1 for a, 5 for b, 6 for c. We plug that into our formula for the discriminant. We get 5 squared minus 4 times 1 times 6, which is 25 minus 24, which gives us a discriminant of 1. Since 1 is positive, we expect 2 real solutions. In addition, 1 is a perfect square, so the 2 solutions will not only be real, but they'll also be rational. No square roots in our answers. Okay, for this next one here, we write down a, b, and c. We plug it into the formula for the discriminant, and we get 25 plus 32, which is 57. 57 is a positive number, so we expect 2 real solutions, and since 57 is not a perfect square, we expect those 2 solutions to be irrational. Okay, for this story problem, we have a 10 feet of framing, and we want to use this to make the largest rectangle frame possible. Remember, we do want to use algebra, not just a guess and check for these types of problems. And then we need to find the maximum area. So we'll begin by drawing a picture of this frame with x and y. And we would recognize then that, well, if the framing is going to be 10 feet, then 2 times the x value plus 2 times the y value must be equal to 10. And then the area is just going to be x times y, and we want to maximize that area. So why don't we just go ahead and we'll solve for y here. First of all, by moving the 2x to the other side and then dividing by 2, giving us y is equal to negative x plus 5. We'll go ahead and replace the y in the second equation with this minus x plus 5. So that's going to give us x times minus x plus 5, which if we distribute is going to give us a parabola of minus x squared plus 5x. So if we can find the vertex of this parabola, that's going to give us the maximum area. So the vertex, well, here's a and b. We'll go ahead and go minus b over 2a. That means that the x value is going to be 5/2. The y value is also going to be 5/2, and we can multiply those two together to get the area of 25/4. Okay, so for this problem, we have a parabola, downward sloping parabola, the maximum height is going to be at the vertex. So here we've got b is equal to 48, a is equal to the negative 16, minus b over 2a is going to give us negative 48 over 2 times negative 16. That simplifies to 3/2. Go ahead and plug in 3/2 again for t, and this is going to give us 3/2 times 48, which is the same as 3 times 24, or 72. 3/2 squares out to 9/4. 9/4 times 16 will be 36. 72 minus 36 will give us a height of 16 feet.